Now, like I say, with graph theory, really the most important thing is for all of you to remember the definition. Definition is very, 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 very important. If you don't know the definition, you will not be able to really do any of the questions. Alright? Especially coming now to Eulerian and semi-Eulerian graph. So tomorrow we're going to look at Hamiltonian. And what we're going to do is, this week we're concentrating on both Eulerian and semi-Eulerian, the Eulerian and Hamiltonian graphs. So we're going to start off with Eulerian graph. Now notice that I have got Eulerian and semi-Eulerian graph. So they are related, but what you have to think of it is the Eulerian is actually a closed and semi-Eulerian is open. Alright? So that's important for you to realize what the difference is. Now, what you need to know after this lesson is understand what an Eulerian and semi-Eulerian graph are. Able to distinguish. Now, there are particular ways that you are expected to answer the questions in exams. Alright? When you're asked to distinguish between Eulerian and semi-Eulerian graph, and able to determine if graph is Eulerian or semi-Eulerian, you must also be able to use that. Your knowledge of Eulerian and semi-Eulerian graph to name the path. Now, remember from last week or 1.5 weeks ago, we talked about walk, trail, and path. Alright? So now, what we're going to do is concentrate on trail. Alright? Trail, you could have trail which is not Eulerian trail, which means you've got graph that you can just go through as in terms of a trail, not repeating the edges. But Eulerian and semi-Eulerian is a particular one. Alright? So the important one, the definition of Eulerian trail, is a trail in a connected graph. No, the word connected is important. That travels every edges in the graph only once. Repeated vertices are allowed, but not edges. So trail, Eulerian trail, is a trail in connected graph that travels every edges in the graph only once. I will show you an example in a few minutes. The repeated vertices are allowed, but not edges. Now, think about open and closed. Open, you start from one vertex and you finish on the other, a different vertex. Now, a closed trail, if an Eulerian trail is closed, which begins and ends at the same vertex, it is said to be an Eulerian circuit. So make sure that you know the word Eulerian circuit. So Eulerian trail could be open or closed, but the closed one is an Eulerian circuit. Alright? That is what you need to really be able to distinguish in the exam. Real? Alright?
What's an Eulerian?
Sorry? Yes, when an Eulerian trail is closed. So you start and finish at the same vertex. Alright, can I move on? Yeah? Okay. Now, here, a connected graph is said to be an Eulerian graph if it has a closed trail, start and end the same vertex, and includes every edge once only. Eulerian graph have only even vertices, and there's no odd vertices at all. So you do have Eulerian graph and semi-Eulerian graph. Alright, let's start off with Eulerian graph. It has a closed trail, start at the same vertex, and when you do the trail, it includes every edge once only. And the next point is important because this is how you could actually determine if a graph is an Eulerian graph. Eulerian graphs have only even vertices. There is no odd vertices at all. Alright? So everything, when you've got a vertex, the edges going in has to be even. Alright? So if you got a fifth one, that is not. As long as there's one odd, it cannot be an Eulerian graph. Alright? It has to be all even vertices. Now, in the exam, you will be asked why is a graph Eulerian graph. You've got to explain in such a way that it is connected and it has a closed trail. It starts and finishes at the same vertex and include every edge. Alright, this is how you should explain it. Not explain that the graph has even vertices. That's only the characteristic of the graph. Alright? So when you explain, if you're asked to explain why is this graph an Eulerian graph, it is said to be Eulerian because it has a closed trail, starts and ends at the same vertex, and includes every edge. Only once. Yep.
What is the second dot point?
The second dot point is just a characteristic for you to observe. For an Eulerian graph, every single vertex must be even vertex. It cannot be odd. You can't remember. Okay. All right. Now, every graph. All right. All right. Every graph, you can see that it's either even or odd vertex. Odd is when you've got 1, 3, 5 edges going in or out, and even when you have got 2, 4, 6 edges going in and out. Yep.
So I thought it would still be like Eulerian if it's only two odd.
No. Anything with odd vertices, it cannot be Eulerian graph. All right. So this point is for you to check. But when you explain why, this is what you should explain. The definition of Eulerian graph. All right. Now, the other word that you need to know is traversable. A traversable graph is one you can draw without taking your pen off the paper and without going any edge twice. So something like this. Remember, when you were young, you would be asked to draw something like this. This is traversable. I drew this without actually lifting the pen off, right? Something like this. Without lifting the pen off. You can consider that as a graph because these are all vertices. Alright? Yeah? So remember the word traversable. You'll come across this word in some of the questions. Now, let's have a look at the first one. Why did I say the graph is Eulerian? Because I can start at any vertex, traverse each edge only once, and return to the starting vertex. Note that all vertices have an even edge. So let's use a red ink. Example, I can go from A to B, start, and then B to C, C to D, D back to B, here, A, and then E, and then back to A. Yeah? That's one way of doing it. Alright, if you don't want, you can start off from E. That way, that way, that way, go back there. I'm stuck. Alright, I can't start from there. Alright, however, if I do something else, I start from E, I can go here, that way, come down here, up there, this way, that way, here, and back to E. Start and back. Alright? So you can see that there are several ways of doing it. There's no one unique way. See what I've done there? The red one just now, I started from A, and then I started from E. Yeah? So in the Eulerian graph, you should be able to start from any vertex, and then you should be able to traverse the graph. So here, I've stated A, B, C, D, E, A, D, B, A is a closed trail, and in this case, also an Eulerian circuit. It is not unique. Other circuits are possible. So in the exam, if you're asked to list one of the circuits, you just have to give one of them. You don't have to give 2 or 3, it's just one. We will go through and make sure that everything is right when we are marking it. So that's possible. When I start from E, E, D, C, B, D, A, B, A, E. That's another one. Alright? There are lots of answers, there's not only one answer. Now, if you look at the second one, this graph is not an Eulerian graph because there's no Eulerian circuit. You cannot start at a vertex, traverse each edge only once, and return to the starting vertex. Alright? Now, you can also notice that here, not all vertices are of even degrees. That is odd, that is odd. Correct? You can try. We can start off with S. That way, that way, that way, that way, that way. There, 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 and there. You cannot go back to S, can you? Without repeating the edges. Yeah? You cannot go back to S without repeating the edges. Agree? Yeah? So, if I start somewhere else, if I start here, I can go here, 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 and that way, that way. I can't even go to the other edge, which is the edge of M, right? Yeah? As M, you can't do that. So here, there is no Eulerian circuit at all. The good check always is see whether there's any odd vertices. Alright? Let's move on. Are you all alright with that? Yeah? Okay, now, here. Oops, what am I doing? Oh, I know why. I animated it. That's fine. Let's go to the next one. Alright, here, I put a note down. All vertices are of even degree. Alright, now to determine if the graph is Eulerian. For a connected graph to be Eulerian and for an Eulerian circuit to exist, the following conditions must apply. Each vertex must be of an even degree. You must start and finish at the same vertex, and every edge must be traversed only once. That's it. So you must satisfy these 3 conditions to determine if the graph is Eulerian. Generally, when I do a check, when you ask, I will just, first thing that I will do is see whether there's any odd. If there's an odd vertex, I know that it's not going to be Eulerian, for sure. Because you cannot start and finish the same. Can I move on? All right, that's fine. All right, that's Eulerian graph. We'll do some example in a few minutes. What we're going to do is going to look at semi-Eulerian in a few seconds. All right, here. Let's have a look at this. I have got 2 vertices with 2 odd vertices. What is this? Can I actually traverse the whole graph? Probably Probably not. This is not Eulerian because it has two vertices with odd degree. So that's how I identify it. That's the first thing I do. I check the vertices. What about the next one? Can it happen? Is it going to be Eulerian? Can you start from 1 and finish back to the same vertex, traverse through every edge, no repeated edges? Can you?
Yeah.
Yeah. First thing I check is whether there's any odd degrees. That's first thing I do is check whether there's any odd vertices. That's none. You can see that every single one, this is even, 4, this is 2, this is 4, this is 4, this is 4, this is 2, this is 4. So every one is actually even. So with even, it is Eulerian because every vertex has an even degree. And you can start from one and go back to the other one. So for example, so you can start from 1, you can go, traverse everyone. I can't start from there. All right? You can see that you may not always start from the same place. There are certain spots that you can start from, but certain spots you can't. All right? Hey, can I do that? No, I can't even do that. So I probably have to start from somewhere here. So sometimes you really have to experiment with it to know that where you can start from and where you cannot start from. All right? So here I've got to start from here or there. So if I start in the middle, I can't really go through and draw the. I can't find the whatever an Eulerian circuit. All right. So you got to think about where you can start. Now we're coming to semi-Eulerian trail now. This time, think about open. If an Eulerian trail is open, it begins and ends at different vertices. It is said to be a semi-Eulerian trail. Alright? Semi is when it is open. You still traverse through all the edges, no repeating edges, but you start from one end and finish at the other end. Alright? It's very typical exam questions that they will ask you, is this a... yeah?
So if there's a graph and all the vertexes have even degrees, does that mean it has to be Eulerian?
Yes.
Okay.
It has to be Eulerian. So semi-Eulerian is okay. With yeah, it is. It has to be. It has to be Eulerian because you will start from one and you go back to the other one because you want to traverse all the edges. Semi-Eulerian, you can traverse all the edges, but you will start from one and finish on the other. All right. So it has to be a connected graph. It has a. A connected graph is said to be a semi-Eulerian graph if it has a semi-Eulerian trail. A graph is semi-Eulerian if you can start at one vertex, traverse through every edge only once, and end at a different vertex. Now, the next point is important is how you identify a semi-Eulerian graph. It must have exactly two odd vertices, that's it. It cannot have 3, it cannot have 4, it cannot have 5, it cannot have 1. Exactly 2 odd vertices. That is such an important point to look at semi-Eulerian graph. Alright? Exactly 2 odd vertices. So you always start from one of the odd vertex and then you always finish at the other odd vertex. Alright? You will get a semi-Eulerian trail. If you start from one vertex, you should be able to traverse the whole thing without repeating the edges and then ended up with the other odd vertex. Can I move on? Yes? Alright, let's go on. So, in this case, the top one, I have got 6 vertices, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8 edges. Alright? Now, is this semi-Eulerian or Eulerian or none?
None.
None. Why?
You have more than 2 odd vertices.
Okay. So the graph is not semi-Eulerian as there's no semi-Eulerian trail. Note that it has more than 2 odd vertices. Now, what I do is here, I show you the characteristic of the graph. But the way I explain is there is no semi-Eulerian trail. Alright? When you explain why, because you cannot traverse all the edges once. Whereas this one, it is a semi-Eulerian. I know that when I showed you just now, it wasn't an Eulerian, but it's semi-Eulerian because that's 1 and 2. 2 odd vertices. So I can start from here. First one, that way, that way, that way, that way, travel, 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 and back to that one. Yeah? Or, if you don't want to do it that way, start from here. You can go here, this way, this way, this way, this way, this way, this way, and that way. Alright? As long as you start from one of the odd vertices, you should be able to go from one to the next one and traverse all the edges. Alright? Without repeating it. You could repeat the vertices but not the edges. Happy? Okay, this is just my animation to show you what I've done, but I've drawn. Alright, determining if a graph is semi-Eulerian. For a connected graph to be semi-Eulerian graph, the following conditions must apply. Exactly 2 vertices are odd. All other vertices must be even. You must start the semi-Eulerian trail at a vertex with an odd degree and end at the other vertex with odd degree. So every edge must be traversed only once. That's it. So I'm pretty sure that the next test will be totally calculator free because it's all this graph theory. I've done it in such a way that I think everything will be calculator free. Now, this graph theory, the only time you need calculator is when you're looking at adjacency matrices. Alright, I'll do it next week. I want to concentrate on this Eulerian and Hamiltonian first. I've seen question coming up practically every year for this. All right, I'll come to some examples now. Can I move on, please? Yeah? All right. Now, example. Here, if you look at the top one, top graph there, are there more than 1 odd edges, odd vertices? Yeah. So it will not be a semi-Eulerian or Eulerian. All right, it's not Eulerian at all. Now, what about the following one? Can you find any odd vertices at all?
Yeah.
2 of them. These 2, correct? Yeah? So you've got 2 odd vertices. Anyone else? No, this is 4. This is 4. 4, 4, and 4. So you should be able to traverse from each edge from one of the odd vertices to the other. Alright? It is not Eulerian, however, it is a semi-Eulerian because it has exactly 2 vertices with odd degree and all other vertices are of even degrees. Okay?
What about the link at the bottom?
Sorry?
What about that link at the bottom?
The link to the bottom,
Isn't
which
it
means there's
5?
1, 2, 3, 4. Yes? So this bit here,
Oh,
you
yeah,
look at that, that's 1, 2, 3, 4.
Yeah.
And here there's 1, 2, 3, 4.
Yeah.
No. Now, if that link at the bottom, if this H at the bottom is not there, alright? It's not going to be semi-Eulerian or Eulerian at all. Alright, now, question that would ask is, if you're given a graph, how are you going to make the graph a semi-Eulerian graph? Right? They are typical sort of question. So you could add another H. Alright? So the typical question is, for example, like you've got buildings connecting walkways. And if you want to make it Eulerian, how do you do it? Build an extra walkway or take away a walkway sort of stuff. Alright? So that's a typical sort of question. Now let's come to this example. Police are patrolling inner city streets to prevent crime. Police officers must determine the best route for officers so that they do not walk along a street more than once. Officers must start and finish at the police station. Describe a route that the officer can take. Now, you can see where the police station is. Yeah? Here. Correct? So you must start and finish here. The only restriction is you must go through all the walkway once. You can go back to the police station again because you can see that if you walk from P to E, you're going to go there and come back again. Correct? That's fine. But you are not traversing, you're not going A to E and coming back from the same route. Yeah? So one of the possible way, when you answer a question like this, what you should do is think about, just, oops, go back. Draw it. Draw it. Let's put this S as a starting point. Alright? Just draw it and so that you know what is happening. So here, I've already drawn a route for you. So you can try the other ways of doing it as well. So this describe a route. From here, I'll say the police station to A, B. Generally, they'll give you police station as P. But because I haven't defined it as P, I'll just say police station A, B, C, A, E, C, D, E, police station, E, F, and back to police station. Alright? That's one way of doing it. The other way of doing it, you can totally reverse that the other way as well. Right? Yep. So you go from police station to F, E, back to police station, back to E, D, C, E, A, C, B, A, back to police station. So you will be asked to give a route. So we will actually in the exam think about, or in the test, there are lots of solutions. So any solution you're given, as long as it's correct. The thing is, sometimes you do get confused. Alright? I know I've done that before. I'll just write and then I'll rewrite the same vertex again, so you've got to be very careful. Yeah? This is probably a complex one. You will, yeah, this would probably be the level of complexity you'll get, or a little bit more. Alright? Yeah. Maybe a couple more vertices. Now explain why this graph is Eulerian and not semi-Eulerian. What did I say just now? Yeah?
It's a closed Eulerian triangle that starts and ends at the same point, and it's every Eulerian.
Thank you. Yeah. So you must explain it that way. It has got an Eulerian trail. It starts and finishes at the same point, and no edges is repeated. That's how you should explain it. Please do not explain it as because all vertices are even. Do not do that. All right? They want the actual explanation. So part C, if one of the route connecting the police station with E was closed. All right. What was the question? Would police officers still be able to patrol every road? They don't have to return to the police station. So in this situation, what I've done is I've just wiped out one of the root. It's closed. So can you look at this? What sort of a graph is this now? Is it Eulerian? Or semi-Eulerian? How many odd vertices are there? 2. So this is one. This is another one. Now here, you've got to start from the police station. Alright? So if you go that way, I can go to F, I can go to E, back to police station, and then A, B, C, that way, back to E, C, D, and finish at E. Yeah? You've got to start at the police station because you're specifically told that you'll start at police station. And you know that you must end up in E because that is the other odd vertex. Alright? Now that's all I have for you today. So hopefully, just a summary, you should remember for a graph or network to be traversable, it must be connected and have 0 odd vertices or exactly 2 odd vertices. For an Eulerian trail, closed trail, and hence an Eulerian graph, each edge must be traversed exactly once. Vertices may be repeated, and the connected graph must have 0 odd vertices. Semi-Eulerian, or an open trail, means each edge must be traversed exactly once. Vertices may be repeated, and connected graphs must have exactly 2 odd vertices. Alright? The semi-Eulerian trail will always start at one of the odd vertices and end at the other odd vertex. Alright, I'm going to stop here. You should have got plenty of exercise to do from our club.